Now let's think a little bit about how this energy is released in chemical reaction. So we said earlier that the chemical bonds store the potential energy of molecules. In a chemical reaction, what happens is the chemical bonds are broken in the reactants and they're formed in the products. It's the comparison of the chemical bonds that are broken and formed that determines whether the reaction produces or absorbs heat. So we have two terminologies I want you to know here, which is that if a reaction produces heat, we call that an exothermic reaction. That's when you mix two things together, and when you hold it, you feel that it's getting hotter. So it's releasing energy to you. Whereas an endothermic reaction is when you mix two things together and you feel cooler afterwards. A most common example of this would just be those heat pack or cold packs that you buy from the pharmacy to treat muscle soreness. They're actually chemical reactions, a lot of times just water mixed with something, and depending on what that something is, it could either generate heat or exothermic or absorb heat or endothermic. Now, how does the release or absorption of heat relate to the chemical bonds? It's as follows. If the bonds in the reactants are weaker, then they will want to form more stable bonds in the product. Okay, so less stable state always wants to convert to more stable state. This is the same idea as if you have a ball that you lifted up the ground. When you release your hand from the ball will want to fall. So the same idea here, if the reactant bonds are weaker, they don't want to stay like that. They want to be stronger. And we say that the weaker bonds are less stable, higher in potential energy, and they want to convert to the stronger bonds which are more stable. When this happens, when the conversion happens, then the reaction will release heat because it's going from less stable to more stable. The opposite happens when you have reactant bonds that are stronger and they're converting to weaker product bonds. At that point, then the reaction would absorb heat or would be endothermic. You might say, why would that reaction even happen if the reactant bonds are stronger already? Well, it turns out that a reaction depends on a couple of factors, one of which is the strength of these bonds. There's a second factor that unfortunately we cannot spend time talking about. It's a little deeper dive into chemistry that this class will cover, but just keep in mind that both types of reactions could occur. So if you look at a reaction like this in the example where AB goes to CD, if the bond in AB is less stable than the bond in CD, well, that means that the reaction will release heat, and then we call it an exothermic reaction. So how strong and how weak are these bonds? We can measure them in experiments, and the strength of covalent bonds that we measure, they're called bond energies. And the values is listed on this table for some bond energies. The larger the number, the more stable the bonds. The way you read this table is this is an HH single bond. This one is a carbon-carbon double bond. We spoke earlier about those hydrocarbons where they can have carbon-carbon single or double or triple bonds, so you can see how the strength of these bonds differ. The triple bonds are the strongest, makes sense, right? Because it's much harder to break. There's just a lot more electrons in between the two carbons that are being shared. The single bond is a lot easier to break. This is carbon, so that's the single bond strength is 346. The unit here is kilojoules, as I mentioned earlier. Joules is one of the units we use to quantify energy, and that's the one we will use for the energy of these covalent bonds. Now we can talk about how to calculate the energy that is released from a combustion reaction. So we're going to use the hydrocarbon propane, which has the formula C3H8, to help us understand this process. There's a number of steps you have to follow. The first is you have to start with the balance equation of that combustion reaction. And then you're going to have to draw the Lewis structure of all the species that are involved, both the reactants and the product, and figure out what kind of bonds you have and count all of them. So it's a tally of all the bonds you see in the reactants and the product, and go to this table to find the individual bonds and what their energy values are and add them up. And at the end you would subtract the reactant bonds total minus the product bonds total. So the answer is positive. You get an endothermic reaction, meaning heat is absorbed. If you get a negative answer, that's an exothermic reaction and heat is released. So let's just take a look at this example of propane being combusted. First step to balance it out looks like this. After it's balanced, there's 5 oxygen, 3 carbon dioxide, and 4 water. Now we have to draw those out as Lewis structure. So you may remember that all the hydrocarbons of alkanes are connected like this, where the carbons are connected together and then the hydrogen's on the outside. So you just follow that drawing for the Lewis structure. Oxygen, you know how to draw the Lewis structure. It's just O with a double bond to another O. Now, of course, there are lone pairs here, but we don't illustrate the lone pairs in this problem because it's not necessary in the calculation. When we do CO2, we have 2 double bonds. Each is a carbon to oxygen. Again, lone pairs are not illustrated here. Lastly, we have water. Also, lone pairs not illustrated, but that's what it looks like, OH and OH. Here, we're listing that there's 5 of these oxygen molecules because that's the coefficient of the oxygen, 3 carbon dioxide, and then 4 waters. So what we need to do is tally up all of those numbers. We have to count here what kind of bonds we have. So we have a carbon-carbon single bond, and there's 2 of them. So we say 2 carbon-carbon single bond. This is on the reactant side. And then we have the carbon-hydrogen single bond, and we can count that. So there's 1, 2, 3, 4, 5, 6, 7, 8, so 8 CH bonds, and then 5 oxygen-oxygen double bond. On the product side, we have 1, 2, 3, 4, 5, 6 carbon-oxygen double bonds, and then 1, 2, 3, 4, 5, 6, 7, 8 OH single bond. What I do then is I look up the numbers for all of those bonds. So carbon-carbon single bond, we have hydrogen-oxygen, right? So you can see here, this is oxygen with hydrogen, so OH single bond, 463. And then we look for the CH single bond, 413. And then we have the carbon-oxygen double bond and oxygen-oxygen double bond. So there you would look down here for oxygen-oxygen and then carbon-oxygen. And then once we total them up, we're going to add for just the reactants alone, and ends up the number being 6,486. And then for the products, it ends up being 8,498. And then we subtract reactants from products. The 6,000 minus the 8,000, and you get a negative 2,012 kilojoules. So when the answer is negative, that means heat is released for every 1 mole of propane. Now, why 1 mole? Because in the reaction, the coefficient of propane is 1. If when you balance the equation, you get a coefficient of 2, for example, for your hydrocarbon, then the energy you calculate is for 2 moles of that hydrocarbon. Of course, we know that 1 mole of propane can be converted to its mass using its molar mass. So when we do that, we get 44 grams of propane. That could then be related to the amount of propane we need to buy for a specific purpose. So now you can see how the whole thing connects together. If I go camping and I buy a tank of propane and it tells me that there is some gallon of propane in it, I can actually calculate how much energy will be produced by the combustion of that propane. Another way to express the amount of energy that propane has is by showing you the heat content, which is just taking the number that we calculate here, the 2012 kilojoules, and then dividing it by the mass of the propane that we use. So if you take 2012 and divide by 44 grams, you get 45.7 kilojoules per gram. So again, that tells you that for every 1 gram of propane that's being combusted, 45.7 kilojoules of energy is released. I want you to work on the same calculation for the energy that you get from the combustion of methane.